Sue Barr from Open Hydro is joining us, and she will discuss their work to use ADCTs and underwater cameras to assess marine species interaction with their Open Center Open Hydro turbine. And finally, Carol Sparling from Sea Mammal Research Unit will discuss marine mammal monitoring at CGen. Go ahead and hit the next slide, Anna. You want to hit the next slide, Anna?
Anna's computer is going slow here for a second.
Oh, okay, great.
Hold on just 1 second.
Sure. While we're waiting for Anna's computer, I'll just say the last thing I wanted to say first, which is I thank you for all of our speakers being here today. We have people calling in from all over the country and all over the world, really. So I think we have a great combination, a great panel for you today. So thank you very much for joining us. And maybe and there it is, thank you. So the way this is going to work is each panelist will take 20 minutes for their presentation, and we'll have 5 minutes of Q&A following each presentation. We're going to try to save time at the end for more of a thematic Q&A. We'll have 10 minutes at the end. But the 5 minutes following each presentation will be for specific questions related to clarifying points that the panelists brought up, or other important questions related specifically to that talk. The way we're going to have you, the participants, ask questions, you'll see in your screen, you'll have a control panel. And on that control panel, you can see a picture on this slide that it should look something like this. You'll see a number of tabs in that control panel. One of them says questions. To ask a question, simply type your question in and hit send. Jocelyn and Anna will be weeding through questions and selecting those that are essentially, if there are 5 questions on a similar topic, they'll pose a synthesis question. They'll send those back to me, and I will ask the presenters those questions orally following their presentations. So it sounds a bit complicated, but I think it'll go pretty well. Anna asked me to say, you might also see on your control panel a place where you can raise your hand to be called on for a question. Do not use that. It does not work very well at all. Simply type in your question, and we'll do our best to get to them orally. And if we don't get to your question, the presenters can also answer them in written form. So that's how it's going to go today. And at this time, I think we are ready to get started and hand it over to our first presentation, which will be Steve Amaral, Ted Castro-Santos, and Paul Jacobson from EPRI. So when you have it queued up, Anna, and when you're ready to go, I think, Paul, you're going to be taking us through it. Go for it.
All right. Thank you. Well, thank you. And first of all, I want to acknowledge DOE for being the primary funder of this research, and my 2 principal investigators on this research, Steve Amaral from Alden and Ted Castro-Santos from the USGS, and they are listed here on slide number 2. EPRI is providing the project management, and Alden Research Laboratory did both strike modeling and literature review related to effects of conventional hydropower and how it might translate to hydrokinetic environment, and also flume studies, and then Ted Castro-Santos led the work at the Conti Anatomus Fish Research Laboratory, where behavioral and strike research was done in the laboratory flume as well. Slide number 3, please, Anna. I want to mention our sponsors. In addition to DOE, who of course was the major funder of this research, we had support from a number of other entities who contributed funding and have been involved in the design of these studies as well. On slide 4, please. Also, in addition to the project sponsors, we had turbines provided as in-kind support by Lucid Technologies, the Welka turbine, and also a turbine from New Energy, the end current turbine, there on the right. Slide number 5, please, Anna. Our objectives for this research was to determine injury and survival rates as well as behavioral effects for fish passing through hydrokinetic turbines. And that was done in three ways: conducting a review of existing information on injury mechanisms, primarily related to derived from conventional hydropower studies, and examining how that could be translated to hydrokinetic turbines. Secondly, theoretical models were developed for hydrokinetic turbines to predict the probability of blade strike and mortality for various hydrokinetic turbine types. And thirdly, laboratory flume studies using 3 different turbine designs in which fish were exposed to operating turbines in the laboratory flume. And those flume studies were done at Conti Laboratory and under the leadership of Ted Castro-Santos, and at Alden Research Labs under the leadership of Stephen Emerald. Next slide, please. As far as conventional hydropower turbines and the applicability to hydrokinetic turbines, the turbine passage injury mechanisms are depicted here in this slide, and they include changing pressure, cavitation, strike, grinding, shear, and turbulence. And those are the locations where that can occur in a conventional hydroturbine environment are depicted in this figure here, provided by Glenn Schott at Oak Ridge National Lab. Next slide, please. With regard to pressure and conventional hydropower turbines, the pressure-related injury can be related to the magnitude of the pressure change, how rapidly that change occurs, and how quickly the fish can adjust, and also the pressure at which the fish are acclimated. And in terms of how quickly the fish can adjust, that's a morphological characteristic of the fish related to the manner in which the swim bladder is connected to the outside of the body or not. And that's what those 2 terms there, physostomus and physoclistus, refers to. An example of a physostomus species in which the swim bladder is connected to the esophagus is the salmon and trout groups, and fish with closed swim bladders that are not connected to the esophagus include fish such as bass and sunfish. Next slide, please. We should be on slide 8. With regard to pressure, hydrokinetic turbines don't experience the extensive and rapid changes in pressure that have been shown to damage fish during passage through conventional hydropower turbines. And another difference is that fish are acclimated to the pressure environment upstream and downstream of the hydrokinetic turbines, unlike the situation with a conventional hydropower turbine. But if a pressure injury is to occur in a hydrokinetic environment, it's likely to be associated with areas of cavitation. If we go to the next slide, that occurs where there's flow separation from the blades, and the relatively low pressure allows for the formation of gas bubbles. And that's associated, it can be associated with hydrokinetic turbines, but only in very small regions immediately around the blades. And the design of the blades and the operation of the turbines is really such that that's minimized. And it can be completely minimized through keeping the pressure at 60% of ambient pressure or greater to prevent cavitation. Next slide. Shear is one of the mechanisms for harm to fish in conventional hydropower environment, and it can occur potentially in a hydrokinetic turbine situation as well, as noted by Glenn Schott in reports in 2007 and 2009. Shear strain rates sufficient to cause injury can occur with velocities, jet velocities of up to 29.5 feet per second. But shears that high are unlikely to occur in hydrokinetic turbines. Where it does occur in a conventional environment, it's located where there are close to boundaries and where there are severe changes in the flow paths characteristic of the conventional hydropower turbines, such as wicket gates and stay vanes. But because hydrokinetic turbines lack these sorts of structures, the potential for shear injury in fish in a hydrokinetic turbine setting is much reduced. Slide 11, please. Mechanical impacts, blade strike and grinding are one of the major sources of impact in a conventional hydropower setting, and that occurs with collisions between fish and the turbine blades and fixed structures, as I mentioned previously, stay vanes, wicket gates, and grinding or pinching between the blade and a hub or a housing is a possibility, as well as abrasion with contact from other stationary or moving surfaces. Blade strike is a major mechanism for fish injury and mortality. And it depends on things such as the blade spacing, the rotational speed, the relative velocity of the fish relative to the blade, and fish length. Strike mortality is dependent upon the shape of the blade as well as its thickness and the velocity with which the fish and the blade contact each other, as well as fish length. And we'll see this more in a little bit. There's a little difference in mortality rates among the various bony fishes, and that helps in terms of transferability of modeling and laboratory results and field results as well from one species to another. Recent studies have shown that blade strike can be greater than survival, can be greater than 90% at speeds up to 12 meters per second. Next slide, please. So we should be on 13 here, yes. The conventional hydropower turbines, blade strike, you can see here there's a relationship between the strike speed, the speed with which the blade strikes the fish, and the survival rate, with that survival rate being influenced by the, as well as the speed with which the blade strikes the fish, the length of the fish relative to the thickness of the blade. And we can see that as the thickness of the blade increases relative to the size of the fish, that survival goes up dramatically. And survival is nearly 100% for speeds up to 12 meters per second, given a fish length to blade thickness ratio that's less than 1. Next slide, please. So if we take results such as those and do predictive modeling, we can see that blade strikes are well established for conventional hydropower turbines, and that recent studies have incorporated strike mortality rates as well to predict turbine passage survival. And these models can be modified to estimate turbine strike mortality and successful passage through hydrokinetic turbines to predict survival rates in a hydrokinetic scenario. Next slide. I apologize for this slide and your copy. The part of the equation there at the top for the probability of strike is covered up. And to the right of the division sign there, you should have a 60 times V sub R as for the equation below for strike mortality. And but a key point here to be made for this slide is that strike mortality is not expected to be a factor at strike speeds less than about 4.8 meters per second for any size fish. Next slide, please. If we continue with the estimation of blade strike probability and mortality for hydrokinetic turbines, there are some assumptions that need to be made, and they relate to the orientation of the fish relative to the flow and the leading edge of the blade, and as well as the velocity of the fish relative to the water. and also the location of passage, whether that passage goes close to the hub or close to the tip of the turbine blade. And of course, the nature of these assumptions changes quite a bit if you're talking about an axial flow turbine, such as you see on the left there, or a cross flow turbine on the right. For the cross flow turbine on the right, of course, the blade is moving towards up current towards a downstream migrating fish on one side, and moving in the same direction as the fish on the other side. So the relative velocities are very different. Next slide. Passage survival rates need to be estimated for the species of interest, fish length, the approach velocity, and the locations of passage, as we've seen in the previous slides. And we also need to adjust estimates for the proportion of fish population expected to encounter the turbines. That is, how many fish actually pass downstream or upstream in an area removed from the location of the turbine. We need to adjust estimates for the species and the life stage, their size group, and the proportion of time that the various approach velocities occur. Of course, in a tidal scenario, the fish may be present and exposed to the turbine when the turbine when currents are slower and the turbine is actually turning more slowly. And then also the area of passage by blade region. For a given distance from the center line, the area affected increases. Next slide. This is a shot showing the lucid spherical turbine, a drawing on the left, and the actual turbine deployed in the Alden flume on the right. And it's a cross-flow spherical turbine, and has 4 blades, about a little over a meter in diameter, and operates between 5 and 10 feet per second current. Next slide. The estimated blade strike mortality, or excuse me, blade strike probability is shown in this figure, and it shows that the probability of strike increases linearly with increasing fish length up to about 350 millimeters, at which point the strike probability is 100%. Next slide. This shows strike mortality, and for the spherical lucid turbine, and you can see that it is strike mortality increases with water velocity, which affects both the velocity of the fish relative to the blade of the turbine and the rotational speed of the turbine.
Paul, this is Simon. Just giving you a friendly one minute or so warning.
Okay, all righty. I will move as quickly as I can here.
It's actually a 5-minute warning. Sorry.
Oh, excuse me, a 5-minute warning.
Oh, much better.
Yeah, there you go.
Okay, all righty. And you can see that for the 1.5 meters per second, survival is 100%. Strike mortality is essentially 0, and that increases with increasing water velocity, and that's for strike mortality. If we look at turbine passage survival, which takes into account the fact that the fish passes the blades twice, we can see that, and looking at passage on the vertical center line for the lucid turbine, we can see that passage survival is essentially 100% for 1.5 meters per second flow velocity, and then decreases with increasing fish length and increasing water velocity. Next slide. With regard to the flume studies, the goal here was to provide information that developers and regulators and resource agencies could use to assess the potential for impacts from these turbines. And that includes describing the behavior of the fish as they approach and pass the turbines, as well as the estimates of injury and survival for fish that don't avoid the turbines and pass through the swept area of the turbine. Next slide. You've already seen this similar shot to this for the spherical lucid turbine. 4 blades about a meter in diameter, and with water velocities of 5 to 10 feet per second, and the blade thickness is about 3/4 of an inch. The other turbine tested was the Welka turbine, and that turbine has 3 blades. It's about 5 feet in diameter, and rotational speeds are relatively slow of 3 to 16 revolutions per minute, and 2 to 5 feet per second approach velocity. Next slide, please. The survival tests that were done for these 2 turbines included rainbow trout and largemouth bass for the Welka turbine, and 2 size groups and 2 approach velocities with each turbine. 5 replicate trials for each set of test conditions with 100 treatment fish and 100 control fish in each trial. The fish were uniquely marked and with a combination of location of the mark and the color of the mark. Fish were retained for 48 hours following the experiment and looking for delayed mortality. And survival was calculated as a ratio of the survival of test fish relative to the survival of control fish. Next slide, please. The behavioral tests were done using the same species and size classes and approach velocities. And there were 3 trials for each set of test conditions, again with 100 fish released per trial. And there were video observations with each test group. I'll skip over this figure of the test facility and go to, we can skip over this slide as well, and go to slide 29. And you can see that here this shows the way in which the fish were injected immediately in front of the turbine to attempt to force the fish through the turbine and prevent them from avoiding the turbine. Next slide. Here are the results of the passage survival for the lucid turbine. And what we can see here is that for rainbow trout, the survival was essentially 100%. And the larger than 100% survival there is a result of the survival of control fish being slightly greater than the survival of the survival of the test fish being slightly greater than the survival of the control fish. Next slide. This slide shows the turbine passage survival as a function of fish length and water velocity, and you can see that the results are very good for 1.5 meters per second and decreasing with increasing water velocity and fish length above 5 feet per second. Next slide. Can you start this video for me, please, Anna?
It's going now.
Okay, great. This video shows fish being injected right in front of the lucid turbine, and if it's showing what it should be showing, you'll see the fish exit from the discharge tube immediately in front of the turbine, and the attempt there was to force the fish through the turbine, and you can see that a good portion of them, nonetheless, are very successful in avoiding the turbine altogether. Others pass through the swept area of the turbine. You will actually see fish too, some of them pausing within the swept volume of the turbine, And in one case, there's actually a fish that exits the bottom side of the turbine and comes back into the swept volume of the turbine before exiting the second time. And if you'll let me know when it's done running.
All right, we moved on to the next slide.
Okay, very good. So now with the Welka turbine, survival was also very high, essentially 100%. And this slide shows rainbow trout. Next slide, please. For largemouth bass, survival was also essentially 100%. And so in conclusion, it's difficult to force the fish. If you go to the next slide, please, Anne, thank you. It's difficult to force the fish through the turbine, through the lucid turbine. The fish exhibited avoidance and swimming either upstream or around the margins of the turbine. The video observations showed that the blade strikes were not indicated when that did occur. The fish weren't stunned or severely injured. Survival was extremely high, essentially 100%. And injury and scale loss rates observed were comparable between treatment and control fish tested with both turbines. Next, I'd like to go to the studies that were done at the Conti lab by Ted Castro-Santos and Alex Harrow. And they used the end current to cross-flow turbine in their study. If we go to the next slide, it shows the test flume arrangement, which was somewhat similar to the arrangement at Alden. And if we go to the next slide, you can see a little bit more detail on the test area with the fish passing through the area in which the turbine was located. Next slide. And we can skip. We should be on slide 39. You can skip that slide as well. Slide 40 shows the flume with the turbine exposed and with water flowing through it. You'll note that the turbine causes a bit of a backwater effect there in the flume, and that so the fish would be very aware of the presence of that turbine. Next slide. This slide shows the survival over time for the two groups of two species of fish that were tested, Atlantic salmon on the top and American shad on the bottom. And after 4 days of being held, the survival for the test fish and the control fish were indistinguishable statistically. And that was for Atlantic salmon smolts passing downstream through the flume, and in the case of adult American shad, fish migrating upstream through the flume. In terms of the speed with which the Atlantic salmon smolts passed through the flume, there was essentially no difference with the turbine in place and out of place. If we look at slide number 42. And with no difference in the rate at which the fish travel along the flume. If we go next slide, please. We go to American shad and their maximum distance with which they ascend up the flume. The maximum extent of that upstream ascent was less with the turbine in place and then with the turbine removed, with antenna 1 being located downstream of the turbine. So there was an effect observed there, and which we might expect given the presence of the turbine, as we saw in that slide showing the turbine operating in the flume. And with that, I think do we have a few minutes for questions, Simon?
Hi, Paul. We're over time. I have a couple quick clarifying questions, which I'll ask you, but we have a couple discussion questions that we'll save for the end. Is that okay?
Okay, sure.
Quick clarifying questions, and if we need fuller discussion, we can get to it. But are the injury estimates on the lucid turbine based on an unloaded turbine spinning at maximum RPM for a particular flow speed?
There was a simulated load on the turbine.
Okay. And if that doesn't answer the question, we can get back to that one in more fuller in written form. Second quick question, are the tested turbines intended for marine open water applications? Did you get that, Paul?
Yes, yes, they are. They are.
So a combination of marine and also
question is yes.
Correct.
Yes, they are. The deployment of the end current turbine that those deployments have been in that I'm aware of have been in riverine environments, but the turbine is suitable for a tidal scenario.
Okay.
And likewise for the other two turbines.
And then one last quick question. I think it's on your last slide that had the blue and well, I think it's on your last slide. And the question was, what are the red lines versus the blue lines bars? Are they different trials?
The if we look at slide 43 for the American shad, those are labeled turbine in and turbine out, the turbine in place or the turbine not in place. But if we go to the slide 42, it's the same. The red bars are with the turbine in place, and the blue bars are with the turbine not in place.
Okay, we have a couple other questions which you can save to the end, but thank you, Paul. At this time, I would like to introduce our next speaker, Tim Brush from Normando Associates, and I'm not sure if Mark Stover from Hydrogreen Energy is on the line as well, but Tim will take us through his presentation on an estimation of survival and injury of fish passed through the Hydrogreen Energy hydrokinetic system. So, Tim, if you're ready, please take it away.
Yes, thank you. Mark Stover was not able to join us today, but asked me to do the presentation for them, which I was happy to do. I appreciate Anna and everyone else that was involved in organizing this. Appreciate the invite and the opportunity. What I'm going to talk about is much more of a case study. Paul just went through sort of well, obviously laboratory and desktop sort of analysis of the broader topics, and then also those specific turbines. This presentation will focus on a particular case study using that involved the Hydrogreen hydrokinetic system. Next slide in. Just a little background on Hydrogreen Energy. They're a relatively new company formed to take advantage of the new focus on hydrokinetic energy and low-head applications. They're based in Chicago. They've just recently secured some additional funding and are moving forward with some interesting projects now. They utilize a modular plug-and-play sort of system that makes installation much more user-friendly and less invasive on the existing structures. The first application of the technology was at Hastings, Minnesota, and that's the one I'll focus on today. In a broader context, they have FERC preliminary permits for 26 projects and 20 pending permits. Their hope is that they can contribute significantly to our energy needs. Next slide, please. The project we'll be talking about is in Hastings, Minnesota on the Mississippi River. Next slide. The project is incorporated into an existing U.S. Army Corps of Engineers lock and dam. It's the Mississippi Lock and Dam number 2, and the FERC official name is Mississippi for the hydro project is the Mississippi Lock and Dam number 2 project. So there's an overhead, the conventional or the Army Corps project with spill gates, the two locks. One is no longer active, one is active. And then sort of in the just left of center of the project is a conventional hydro project that the city of Hastings, Minnesota installed in the late 80s, thereabouts. It's a 2-unit conventional project. Hydrogreen partnered with the city of Hastings to install their hydrokinetic unit, and it is placed in the tail race of the conventional hydro project, as labeled there at the bottom of the photo. Next slide, please. This project ended up with a 23-year license for the FERC license for the hydrokinetic portion of the technology. They installed a vertically stackable 100 kilowatt system. The actual output depends on the velocities in the tail race of the conventional project. Of course, they're generating at an existing dam, so no civil structures were needed for this. They worked very closely with Army Corps of Engineers and FERC and other regulatory agencies. We received this actually was done through a license amendment, and it happened relatively quickly in terms of FERC permitting, as in 8 months. And this is the only FERC licensed hydrokinetic project in the U.S. at this time. Next slide, please. A few photos of their unit and its installation. The first photo at the top left is right after fabrication. That's a 12-foot diameter unit. They loaded it onto it's suspended from a barge in the tail race. So they loaded it on the barge downstream of the dam. The dam's in the sort of in the background of that upper right photograph. So they had a landing area there that they could work from, and then using a tugboat pushed the barge up into place, anchored it, and then it was ready to roll. And obviously, as you're looking at it, it's the unit can be raised or lowered below the surface of the water using that superstructure that suspends it. Next slide, please. They were fortunate. They had FERC Commissioner Phil Moeller come out and for sort of their opening day, and he flipped the switch for them. And that photo on the right shows the barge with the turbine unit submerged and in operation. Next slide, please. A few of the specifications important for the work that we conducted for them: 12-foot diameter runner, very slow, 21 RPMs, 3 blades, which is important as far as impact, mechanical impact. The less structure you have in the unit, the more favorable it is for fish passage. And there's no pressure effects because there's no head. Next slide, please. The approach we used for evaluating the fish friendliness of this unit was the Heisey turbine tag methodology. It involves control and treatment groups. The number of treatments, obviously, depending on the number of variables you're testing. In any case, both control and treatment groups are marked with a defilated balloon tag, a radio tag, and a VI, that's visual implant, or a Floyd tag. The balloon tag is the primary tag in that it allows us to recapture the fish after they pass through the unit. The radio tag is used to help locate the fish before they rise to the surface so that we can retrieve them very quickly. And the VI tag is sort of a backup in case the balloon and or the radio tag is lost, or they're both lost, so that we have a way of identifying that fish uniquely. So the basis of this approach is to be able to introduce fish and recapture a very high proportion of them so that they can be examined in hand for injury and then held for survival evaluation. And I believe in this case we recaptured on the level of something like 99% of the fish that we introduced. This allows us to have a relatively small sample size because our precision is it allows for very tight precision with a small sample size. The treatment fish are usually passed right out around the turbine and released in the same area, in the area of where the turbine discharge is. Next slide, please. It's just a very rough schematic of the turbine and where we introduced the fish. The red structure there is our induction tank and tube. In this particular study, we because our sample sizes and our treatment groups were limited, we chose what we considered to be the most conservative route, or the highest mortality, low survival route, that being close to the tip of the turbine blade. There you can see some of the dimensions of this unit, relative dimensions. And next slide, please. Here's two photos of sunfish with the tags prior to release, prior to inflation on top, and then after recapture below. The techniques works well in that in many cases our recovery boats are sitting right essentially on top of the fish when right adjacent to where the fish surfaces because of the radio tag attachment. Allows for very quick recovery and usually on the scale of 2 to 5 minutes or so in this case, because it's such a small unit and easily accessible. I think our recoveries were more in the realm of about 1 minute or so after release. Next slide, please. Just a photo recapture of a big-mouth buffalo, adult-sized fish. In this case, we used 4 balloons to bring that big fish to the surface. Next slide. Okay, here's the meat and potatoes, if you will, the results matrix. We looked at essentially through the study plan development negotiations with the agencies and virtually all the, well, two or three different state agencies, 2 or 3 different federal agencies, and then FERC were all involved in the planning and development of this. What we came up with were 2 different general size groups, small and large, if you will, and those were represented by this series of species, these series of species were employed to represent small and large and other, these were surrogates for other species as well, excuse me. We had very high survival as we anticipated because of the size of this unit and its slow revolutions per minute. Confidence intervals were pretty tight, and the size groups utilized are in the bottom row there. So the small fish, roughly 6 and 5 inches for those respective groups, and the ranges of 4.5 to 9.5 inches. And then the larger fish were in the 21 to 24 or 17 to 24 inch range, means, and then ranges of about 15.5 to 28 overall. So some big fish that we were handling through that unit. We curtailed the results of the smallmouth buffalo and bigmouth buffalo. In those cases, actually, our treatment survivals were very slightly higher than control survivals, but we cropped it at the control survival value. So in comparison to the way Paul presented his data, effectively we had 100% more 100% survival across all those groups. We just presented it slightly differently. Effectively, it's about the same. Next slide, please. Hydrogreen's look into the future with the recent financial backing that they received earlier this year. They're using the same sort of turbine technology, but focusing more on lower head applications than in-stream flow. And primarily they're looking at Army Corps lock and dams, but could also be other existing infrastructure. Similarly, a modular, vertically stackable system. Their approach to this strategy and development of this has been to have minimal interference with various aspects, including navigation and the core structure itself. And then to minimize any downtime of any of the facilities due to installation, they essentially prefabricate as much of it as they can before getting on site, and then move it into site and drop it in with minimal impacts to the project's operation.
Hey, Tim, just
this
3-minute warning here.
I believe that's about the bulk of it. Next slide, please. This is just a tribute to our crew that did this work, very hard-working fisheries crew. And then on the right, that's Mark Stover and Heidi Watto of Mark Stover, Hydrogreen, and Heidi Watto of Hatch Energy. She assisted with permitting aspects of this thing. And my contact information's there if anybody's interested in follow-up to this. And with that, I'm complete.
Great. Thank you, Tim. I have one question in for you so far, so if any of you are in the audience and you have a question, now would be a good time to type it into your box and hit send. Actually, now I have two. The first question is, are you absolutely sure all fish went through the Hydrogreen turbine, or might some have avoided rotor passage, as in the Lucid study?
We're virtually certain. We did some, before we actually did the treatment group, we put a handful of fish through and essentially did some pre-testing. I believe we also had a video camera with us and were able to get a good sense that those fish were moving through. The velocity with which they're pushed through is pretty high too. They're essentially pumped through that induction hose.
Great. Second question just came in. Were there any ESA threatened and endangered species at the Hastings, Minnesota site? If so, could you please brief us on the consultation?
This is a few years ago now, but my recollection is, as far as fish, there were not. There were some other mussel-related things and that sort of thing, but I don't think we had any endangered fish.
Okay. Another question. Slide 13. Do you want to flip to slide 13, Anna? It says no injuries observed. Any idea what caused mortalities?
Well, okay, that's a good question. I forgot to even mention the no injuries observed. We've come up with a sort of a maladies scale that Paul Heisey, the guy that sort of champions these studies for us, has developed, and I'd be hard-pressed to explain the details of that. But relative to control fish, there were no injuries observed. The survival values of 98.1 and 99, I believe, essentially then are artifacts of the way we've approached the data now. So essentially taking a conservative approach when the treatment group survival was greater than the control group survival. when that happens, we've taken the approach of cropping it at the, essentially selecting the control group survival as a more conservative approach. So essentially there weren't any dead fish.
Okay.
Do people follow that? It's essentially the same point estimate formula that Paul presented. It's the survival of treatment fish over survival of control fish. And if the control fish group survival is less than the treatment group survival, you end up with a survival point estimate that's greater than 100%. So we just crop it back and use the control group survival as our estimate in that case.
That makes sense. If there are further questions on that, feel free to type it in. We can get to it in the 10-minute Q&A. You have a couple more questions. Are there plans for future more in-depth studies, i.e. greater number of fish, more species? And did the Corps of Engineers require the study to be able to install this test site?
My recollection is the Corps did not require this. It was a requirement of, well, FERC ultimately required it, but the agencies we dealt with in most detail were Minnesota DNR, Fish and Wildlife, U.S. Fish and Wildlife Service, National Park Service, and the Minnesota Water Quality Agency. I forget the name of that agency. But your first question, I think, were there any other plans? At this particular site, there are not.
Okay. Last question I'm seeing, did the speed that the fish were sent through the rotor blades affect the outcome when compared to fish just swimming at normal rate? So does that make sense? Do you get that?
Yeah. In other words, if they were injected at a speed faster than if they swam through natural. Well, I don't know, and I don't know that we could test that, but I don't believe that would be an issue. I mean, the passing through, and it's one of those field-related items that that may be hard to get at, but as far as I'm concerned, it's the best approach we have at conducting a field study of this type.
Great, and we have one minute left. I might ask you one question.
Sure.
And this is just sort of a comparison question. Obviously, Paul is talking about doing some similar experiments in laboratory setting. You're working in the field setting. I'm wondering if you have any comments on sort of why you did that, how you did that, what kind of differences you might expect, any particular challenges worth noting?
Is that to me?
Yes.
And it's any particular challenges worth noting in conducting the field study? Is that essentially it?
Versus doing this kind of thing in a laboratory flume.
Oh, well, I know all those guys, Ted, Paul, and Steve very well, and the work they're doing also poses many challenges that I'm sure they could list as well. But in the field, it's often the challenges. One of the challenges is often procurement of test specimens. And of sufficient sizes and numbers to be able to conduct this. We were fortunate in this case that the agencies allowed us to purchase the fish from vendors approved in Minnesota. That there's logistical questions with that because of disease and all sorts of things, but we were able to work that out. What that does for you, it makes it greatly much more convenient, and consistency with size groups is important when you're trying to conduct something like this. Other than that, this particular location was relatively easy to work at. I mean, when you compare it to some of the other sites that are far larger, like the Army Corps dams on the Columbia River, we do a lot of work in those projects, and this site was relatively easy compared to those. So,
great. Thanks, Tim. At this time, I think Anna is pulling up Sue Barr's presentation, and Sue will talk us through work on open hydro fish response to the open center turbine. So, Sue, without further ado, please take it away.
Great, and good afternoon, everybody. I hope you can meet me okay. You can hear me okay. I'm going to get Anna just to turn my slides over as I go along, so hopefully that won't interrupt too much. So if we could go to the next slide, please, Anna. So really the aim here is just to give you a brief overview of who we are, who Open Hydro are for those of you that aren't aware. Some work that we've been doing on monitoring our own particular technology, and some methodologies we've been using to look at the interactions between the open center turbine and marine animals, both pelagic fish and marine mammals, to try and ascertain really whether we're seeing any impacts, whether those receptors are being impacted. I can show you the findings of that work and also give you an overview of work that we're going to do in the future in order to start substantiating that work a little further. So the next slide, please, Anna. Just to give you an overview, and hopefully this video will work for us, for those of you who don't know who we are or the technology that we use, Open Hydro is an Irish technology developer. We've developed a tidal technology known as the open center turbine. This turbine is a bidirectional permanent magnet ring generator turbine. That is, it operates as a bidirectional turbine in marine currents, and so it's in actual tidal flows. This video should have shown you the deployment technique that we have. Effectively, the turbine works on the basis of magnets moving past coils and works in both directions. But I think we're going to struggle with the video there. So perhaps if we move on to the next slide, Anna. So ideally, what we wanted to do was use the turbine that we have mounted at the European Marine Energy Centre up in Scotland to try and ascertain what kind of interactions we were having with the baseline ecological conditions and to see whether we could actually describe those. We've been doing a lot of work globally in terms of the sites that we're assessing for potential tidal energy development, but also in trying to understand the science that's available to us in order to make decisions and in order to take forward our regulatory advice and gain consent for site. So one of the things that we recognised very early on in the stages of development of tidal energy sites is that effectively marine environments, marine high energy environments like those where we're seeing tidal velocities that are of interest to tidal technology developers tend to be very poorly understood in terms of their ecological baseline, in terms of the ecological behaviour within these sites, and in terms of the ecology per se. They're very difficult sites to sample and to understand because of those high energy dynamic environments, but that also makes them very interesting in terms of the ecology that is present in those sites. So we can turn to the next slide, Anna. One of the other areas that we found particularly interesting is actually determining effects on receptors. We know that renewable energy in the marine environment in particular, both offshore wind, wave and tidal energy, have all been fairly new. So we haven't had projects in the water for a very long time. When we were looking at how to determine what effects the open center turbine would have on the receiving environment, we reviewed the interactions with other renewable energy devices in order to try and ascertain where best practice was being applied, what techniques and what equipment was available to us in order to determine effects. What we found is that because of the stage of the industry, the number of technologies in the water, and the understanding of the baseline ecology, that there was very few techniques and technologies available to us in order to understand these interactions. There's large gaps in the knowledge on the specific ecological interactions with tidal technologies, purely based on the fact that these in-stream marine applications are very few and far between. There's only a handful of devices in the water, so the collection of data has been stymied almost by that. And the commonly used survey methods can often be inappropriate. For example, what's not referenced in this particular study would be measurements of sound, another impact that we needed to consider, and finding equipment that can actually measure sound in high energy tidal flows has been difficult, along with just understanding the ecological interactions. So there was a number of key challenges here. Next slide, please. So to give you a little bit more information about the place where we undertook the work and also the work that's been ongoing, you'll see the bottom left-hand picture there. This is the open center turbine on our research structure. So this is the facility that we use to test all of our devices at the 6-meter scale. This has allowed us to really prove our technology in terms of having that generator lowered into tidal streams. The tidal streams at this particular location, which is off the north coast, the very north coast of Scotland in the Orkney Isles, is very dynamic. It's very challenging. We see tides there in excess of 4 meters per second. We've had a device in the water there since 2006, and this has given us a really good opportunity to not only test and prove the technology and take it through an iterative engineering process, but also to look at how that technology, based on the research structure, is interacting with a very dynamic tidal energy device. So this is the European Marine Energy Centre. It's specifically designed for testing of tidal energy devices, and it's based up in the Orkney Isles there. We decided we've undertaken a whole suite of environmental work there, but the key one in relation to this particular study was undertaken between June and July in 2009 and 2010. So we go on to the next slide, please. The methodology that we used, as you can see there, there's a schematic diagram of how this turbine is lowered into the tidal flow. This isn't the commercial application that we'd use going forward. We intend to mount those particular turbines, so the white circular turbine, on subsea bases. But what we wanted to understand in the first instance is, are we seeing anything approaching the front of the turbine? Are we seeing any entrainment or issues, or are we seeing any collision issues associated with a rotating turbine in excesses of 8.5 knots? We were very fortunate insofar as we've got good visibility in that water, of course during the hours of daylight. And whenever the turbine is lowered, you'll see from the schematic there that we have a camera mounted possibly about 2 meters from the face of the turbine. Now this camera allows us to feed back to a XXX8 channel DVR. So effectively, during all the states of operation, we can view the front of the turbine. So whenever the turbine is lowered into the water column, we have thousands of hours of footage of really observing activity at the face of that turbine. What we wanted to use was use a continuous video system, so we could monitor different states of the tide, and really recognizing that we would only be able to assess a segment of that data, finding the correct statistical method to pull out randomized photographs to give us a good view of what was actually happening at the face of the turbine. And this allowed us to really look at fish counts, look at the state of the tide, and assess whether or not there was any correlation between fish behaviour year on year, or whether we were seeing anything that was relevant to the turbine operation, or whether other abiotic factors were really affecting the fish aggregation around the platform. Next slide, please. So again, I think I've probably just touched on our objectives. It's probably fair to say that in the 5 years that we've had the turbine up at the European Marine Energy Centre, we've observed very little in terms of environmental interactions. The one species that we do see aggregate around the platform is pollock, P. pollicus. It's a very common species, a pelagic species similar to cod, which will feed in the water column and really is of commercial interest in the area that we're looking at, which is the north coast of Scotland. We very much wanted to focus on this particular species because it was the only species we observed, and we really wanted to understand what the responses were to the turbine and assess abundance in relation to both flows and time of day. So really what we're looking for here is, why are the fish aggregating? What are the other variables around fish aggregation that could cause them to be there? Is it time of day? Is it state of the tide? Is it time of year? Is it water temperature, etc.? So to do this, we were integrating the video camera technique with ADCPs, acoustic Doppler current profilers. So these are pieces of equipment that allow us to measure the velocity in water flows by looking at particulate matter. Next slide, please. So the velocity measurements, in order to understand both the performance of the turbine and also the fish behavior, we wanted really to use the ADCPs. Now, the turbine is in an area where it faces both north and south, and we had an ADCP pointing in both directions, so we could look at upstream and downstream velocities. That helps us with both the hydrodynamic analysis, but also in terms of understanding the tides around that turbine. So we're using what's known as a Nortec aqueduct 2-beam ADCP. It allowed us to have continuous horizontal velocity raise measurements every 10 seconds. So this gives us a very dense data set in order to assess tidal flows around the particular turbine. And what we wanted to look for was the mean fish abundance, so the geometric mean over different counts at different points in the day. This was really to assess the relationship between the fish abundance count and the velocity using statistical analysis, but it also allowed us to look at where there aren't associated activities and abundances with fish. It's say in relation to time of day or the particular time of year. So if we go to the next slide, please. So the number of results, you would see from the video images captured at the bottom of this screen, we didn't see the fish particularly often, and what we were trying to understand was what is causing the fish to aggregate there. So if we look at the central image, this would be a sort of high density aggregation of pollock on the downstream side of the turbine in tidal flows. Very notable, we managed to get species identification through linear lines and through mouse, looking at actual mouth apertures on fish. And we're almost 100% certain that the only species we have seen is pollock. The total number of hours in daylight where we could observe, actually observe the turbine were 261 over 2009 and 2010. It was only the singular species that was found for both survey years at the device. You'll see from further work that the assumption is that the fish, as with any anthropogenic structure in a marine environment, were attracted for refuge or feeding opportunities. So what we did observe is that when the fish were present on the downstream side of the turbine, it was an optimistic use of slowed velocities. They were actually picking off phytoplankton and zooplankton that had been slowed by the turbine. And in total, the actual percentage of time that we were observing fish in the total observations was very small, 13% of the time in 2009 and 8% in 2010. So we saw a decreased aggregation or abundance of fish in 2010 as compared to 2009. So next slide, please. We then went on to use two forms of statistical models in order to understand the effects around this. So this is using statistics really to try and assess whether or not there is any recognizable patterns within the fish abundance data. We had a number of interesting data sets within this. So running statistical models, we needed to use two different types of model in order to understand that. Both the generalized linear model and the generalized additive model, which statistically allowed us to look at these variables and really start pulling out some quite interesting results. The abundance response, so this is the number of fish that we saw year on year. During 2009, really the range in those photographic stills that we saw, given that you're looking over quite a restricted area at the face of the turbine, they did have a range from 0 to 46 in 2009 and 0 to 11 in 2010. So we were seeing significantly less abundance counts in 2010. But again, they fluctuated very much against each hour, and the survey data for both years with no clear observation was observed. So we're seeing in that 8% and 13% positive abundance count periods, very high fluctuations in terms of the number of fish that were present at the device. So if we move to the next slide, please.
Sue, this is Simon, just giving you about a 4 or 5 minute warning, and if there are participants who have questions for Sue, now is a good time to type them in and hit send on the button.
Thanks, Simon. So quickly to move through the results, the statistical results really showed us on the basis of the two models that we ran, the GLM and the JAM model, they gave us one variable which stood out as having a very high response to fish abundance, and that was really around velocity. So what we're finding here is that the fish presence or absence was very much related to the speed of the water flow. Now for any fishermen there, this often makes sense. Fish tend to move into areas of shelter when the velocities increase. What we were seeing, interestingly, is that after 1.3 meters per second in 2009, there were no fish at any point during the survey period. And after 1.8 meters per second, there were no fish in the 2010 period. In general, there were very few fish present after 1.3 meters per second, so around 2.5, 2.6 knots. Obviously, fish behave in accordance with behavioral ecology, and so there was some unexplained variance, which could be due down to the sampling methods. But we're pretty sure that velocity has a very strong effect on the abundance of fish. So the next slide, please. So again, we know that fish show natural variability. We only ever observed one species, and during this we did not observe any marine mammals, nor did we observe any collisions or entrainment. Generally, the velocities increase, the turbine starts to turn, and what we were seeing that the fish were not present at the same time as when the turbine was operational, due to that association with the velocities. Next slide, please. So to take this further, we intend to use the research structure for as long as we possibly can. It makes good sense to a technology developer to be collecting data and to strengthening these models and understanding those other variables. So we would hope to continue the work. We'd like to get a larger data set. We'd like to do some additional camera surveys and also start adding in other abiotic factors. So looking at perhaps the level of zooplankton or phytoplankton in the water, the temperature, weather conditions, things like wave state and seasonality, to really start solidifying this a wee bit further. On the next slide, please. We are working with Imperial College London, and the paper is about to be put out into the peer review press following September. I'd just like to thank the DOE for inviting me along to speak about this, and also my PhD student at Imperial College London, who's the co-author of this paper. So I hope that was useful and brief enough to keep me within the time, Simon.
Perfect. Thank you, Sue. And we have a flood of questions coming in. I want to also remind our presenters that Jocelyn's working hard behind the scenes to assign questions that are coming in that we can't get to orally. So as the presenters receive questions from Jocelyn, answering those would be helpful. And we'll try to get to the questions for you, Sue, in the time we have. And I'll just go down the list for now. I had a couple different questions that might be related to this, and that was biofouling. So I think one of your slides might have shown a brown object sort of in the rightmost part of the photo, and I thought that might have been a kelp frond, and someone was asking about that. And yeah, so figure 5, examples of photographic stills captured from the video surveys. On the rightmost photo, there's a picture of what looks like macroalgae, and the question was, will biofouling in the future will biofouling be reviewed for assessing more intensive aggregation of fish species?
Yeah, I mean, it's one of the areas that we need to look at, and certainly we know that we use antifoulants on the blades of the turbine, for example. So we're not observing biofouling at extreme levels there. For this particular structure, it is a research platform. So what we have observed is some growth and some coverage on the piled structures, as you would expect on a standard monopile structure, whether it be a wind farm or a tidal turbine research platform. It's been very, very sparse. The environment there is very dynamic. We do see algae inshore of the area, and we do get significant amounts of, I suppose, debris in the water that will be brought up during storms, etc. And it's an area that we're going to have to consider when we move out of, say, the more photic zones into deeper water. These are areas that we're going to have to consider. And we're hoping that there's ongoing research globally in terms of reef effects as well, which is the direct correlation between your biofouling and fish aggregation. So hopefully we'll take this work forward and it will be considered.
Great, thanks, Sue. And then another question was on whether or not there were any differences in fish behavior between flood and ebb tide.
Again, this is another area that we want to look at. Generally, what we see is the same behavior in both directions, but you would have seen that the camera is actually fixed. And so when the fish move to the other side of the turbine in the reversing tide after 6¼ hours, we have less ability really to observe the behavior there. We can get the presence or absence shots, but in terms of behavioral ecology, it is different. What we have observed is that they are certainly, as you can see from the face of the turbine, it's a very solid structure. And what we see hydrodynamically from the computational fluid dynamics that we do is that the velocities on the lee side of the turbine tend to be much slower. We get a speeding up of water through that center open hole around the outside and over the top of the turbine. But at the back of the blades, I suppose, in the lee of the blades, there is a reduced velocity there. And we pretty much suspect that will be in both cases, whether on the ebb or the flood, we're going to see a slowing of water and some opportunistic feeding ongoing. But again, it's another area we need to look into.
And there's a similar question about day and night, as far as any differences observed between day and night, and if this actually maybe links to another question, which is talking about non-visual observation technologies like using sonar. Did you guys have any ability to observe differences in fish behavior between day and night?
We didn't. This is purely during daylight hours. Again, another limitation of the study. I think one of the key issues will be these non-visual techniques and the ability to use them for assessing behavioural ecology in an effective way. It's something that certainly we would be working with, with colleagues in the United States. We'd be working with colleagues in the UK and in different research laboratories to try and find the best technology for doing this. I don't think it exists in the marketplace yet, and I think it's something that all tidal technology developers will be looking at going forward.
And just to put a plug in, that will be the subject, one of the subjects of our next webinar on September 14th. So I think that's a great conversation to have. There are a number of questions around the theme of sort of direct interactions or direct strike type of situations observed. One was, did you observe fish swimming through the middle of the turbine? And then another one was, were there any direct fish-device interactions observed or detected?
We had neither. We've looked through a lot of footage over quite a considerable number of hours, and we have not seen fish interacting with the turbine in any way. They tend to hold station on the lee side. They're not tending to use it as false shelter by moving through it. And what we're not seeing is any I mean, the hydrodynamics don't allow for an entrainment or a pulling into the turbine. But in general, the fish tend not to be present when the turbine is operational. But we've seen no direct strikes, no direct interactions either by any pelagic fish species or marine mammals. So it's promising, and what we want to do is really, as been stated earlier by other interacting parties, that we need to push this work out and understand more about the interactions. And nighttime interactions would be very interesting, along with having some kind of non-visual technology so that this is effectively running 24 hours to give us some results. But to date, we haven't seen anything that's caused us any concern, which is promising.
Okay, two quick questions, and then we'll move on. First, what is the cut-in speed for the open hydro turbine?
It very much depends on the environment that we're pulling it into. For this particular environment, we're looking at about 1.4 meters per second. For different environments and different turbines, it will very much depend on the velocities and flows. So, for example, we have had a 10-meter turbine in the Bay of Fundy, which will have a different cut-in speed to the 6-meter turbines. We've tested, we're up to the 7th 6-meter turbine on that research structure, and obviously as we're improving the technology and going through the engineering process, those cut-in speeds will change. So very dependent on the receiving environment, and I suppose that's one of the benefits of the open center turbine. We tend to engineer that to the tidal velocity, the seabed geology, the swept area, etc., etc. So it's variable, unfortunately.
Okay, and final question. This is a conglomeration of a couple. We're around what other species you might have observed, whether or not pollock were the only fish present, and did you observe any marine mammal species in the area or any interactions from those?
So pollock were the only species. We started the work initially because we were observing, we have a platform above the turbine, and we were observing fish from the surface in about 2008. When we eventually started to do some identification work with the camera, pollock is still the only species that we've observed at the actual turbine. The area of the Fall of Warness is known for marine mammals. We have orca, we have basking shark, we have Atlantic white-sided dolphin and minke whale. The area is observed by a marine mammal observer from the European Marine Energy Centre, and they track the movement of large cetaceans and also seals through the area. We haven't seen any marine mammal interact with the device. We have some interesting photographs from a cable-laying vessel. A pod of orca went through the area. The turbine was in the raised position, and they went very close to the piles. But again, the turbine wasn't in the water at the time, so we have not seen any seals, any dolphins, or any orca interact with the device whilst it's been operational in the hours of footage we've looked through. So no, we haven't seen any what you could call interactions, and certainly no impacts.
Hi there. It sounds like we may have lost Simon momentarily, but thank you very much.
I'm sorry. I was on mute there. I was just saying thank you to Sue. I think we're going to move on now to Carol Sparling from Sea Mammal Research Unit. And looks like Anna has her slides coming up now, and Carol's going to talk about monitoring marine mammals, so transitioning to that very question that Sue set us up for at CGen 3 years post-installation. So Carol, please take it away.
Hello, I'd like to thank DOE for the invitation to give this presentation today, and also just to say thanks to the other presenters. I've really enjoyed listening to their presentations this afternoon. I'm going to talk to you today about some work that we've been involved in with marine current turbines, developers of the CGen tidal turbine, with its installation in Strangford Narrows in Northern Ireland, over here in Europe. Could we have the next slide, please? Okay, well, we're just waiting for the next slide to come up. Yep. Certainly, at least in a European context, where I'm based, Scotland is at the forefront of marine renewable energy potential. And the government, the UK and the Scottish government, have set some fairly ambitious targets to meet electricity supplies from renewable sources. There is a great deal of uncertainty over the effects on wildlife of tidal turbine devices, and I think that's certainly recognised by the amount of good work that's going on worldwide to try and address these uncertainties. And unfortunately, unlike some of the work that's been presented this afternoon, there are experiments that you can't do with marine mammals to assess the strike mortality and effects of collisions with devices. So we're fairly relying on empirical measurement from existing devices like the CGen device and the device that Sue's just been talking about. So if we could have the next slide, our focus today is talking about the Strangford Lough project. Strangford Lough, Northern Ireland, is a sea loch that's connected to the Irish Sea by a very, very narrow inlet. The Sea Mammal Research Unit has been involved in the project since before installation, since around 2005, 2006. And we've been providing scientific advice, monitoring and analysis and interpretation services to marine current turbines, working with the regulators, the statutory advisors and the developers to try and progress this program. Next slide, please. Strangford Lough has been identified as a site which supports internationally important examples of particular marine and coastal habitats and species, and accordingly has been given the dual status of a European Special Area of Conservation and a European Special Protected Area. Focusing on marine mammals, the harbour seal population is actually one of the site features that were identified as being potentially vulnerable to impacts and activities associated with the turbine. And so, accordingly, key objectives for the monitoring program for the device installation were that the presence of the turbine did not have a significant impact on the integrity of the harbour seal population or the abundance, diversity, and integrity of other communities. The presence of harbour porpoise is also a feature of the SAC, and harbour porpoise are protected in their own right as European protected species. The yellow dots on the slide just show the location of individual harbour seal haul-outs within the loch and the narrows. Harbour seals return to the loch to haul out between foraging bouts and also to breed, and there's a breeding population of between 200 and 300 animals in the loch and narrows itself. Next slide. So I'm just going to talk a little bit about the turbine now. It's the first commercial scale marine current turbine to extract energy from UK tidal flows. It's a 1.2 megawatt device. It sits in water of an average depth of 26 meters. The rotors measure 16 meters in diameters and have a maximum speed of 14 RPM, which equates to a tip speed of 12 meters per second, and operates in a mean spring current of 3.7 meters per second. And it was installed between April and July 2008 and became operational in July 2008. Next slide. So today I'm going to talk to you about the monitoring program for marine mammals over the course of the project. We've been monitoring impacts on marine mammals at a number of spatial and temporal scales, including techniques such as using active sonar mounted on the device to look at underwater interaction, underwater targets. We've had a program of visual shore-based surveys observing marine mammals at the surface around the device. We've also been doing acoustic monitoring for harbour porpoise in the narrows and inner loch using T-pods. And we've carried out some seal telemetry studies looking at behaviour of animals, of seals, as they transit in and out of the loch, and the effect of the turbine on that behaviour. And we also carry out annual aerial surveys of seal haul-out sites on a regional basis. Next slide. Today I'm actually going to focus on, or try and get through at least some results from 3 of those. I'm going to focus on the results from the visual shore-based surveys, the acoustic monitoring of harbour porpoise, and the seal telemetry studies. I'm going to start off by talking about the shore-based observation work. So the next slide, please. Now this, don't worry too much about this slide. It's not a particularly good representation. It just, each dot on this slide is a marine mammal sighting in XY space. The turbine is actually located around cell E4, if you can make that out. I just want to point out at this stage that we've actually seen no decreases in abundance of seals or porpoises between the baseline and operational periods. But what we have seen is some interesting patterns in distribution in relation to turbine operations. So if we go to the next slide. The next slide should show some distribution figures. It's showing the same distribution as in the previous slide. So it's spatial. Each grid cell shows a location in relation to the turbine. The turbine is denoted by the star in cell E4. The panel on the left-hand side shows all the cells that actually had a significant reduction in average seal abundance when the turbine was on relative to off. And the panel on the right-hand side actually shows cells which had a significant increase in seal abundance when the turbine was on. So despite not seeing an overall decrease in the numbers of animals seen around when the turbine was on, there was a significant redistribution of animals within a scale of a few hundred meters around the turbine. Now, the same, I'm not going to present the results for birds here, but the same picture was seen for several bird species with very sort of small scale local changes in distribution in relation to turbine operation, but in the same case, no actual changes in overall abundance between periods of operation and non-operation. So I'm just going to flick through the next two slides that just show the density surfaces for grey seals, and that just shows the increase in, oh, can we just go back one please? The grey seal just shows that there were much more sightings. The observer was actually situated on shore on the top right position of this plot, so actually more sightings of grey seals were closer to the observer, whereas the next slide, which shows the distribution of harbour porpoise, shows that more sightings of harbour porpoise were actually seen in the central channel closer to the turbine than to the sides of the channel. There were no changes in distribution with harbour porpoise or grey seal, a relative abundance with time or with turbine operation, which was relatively encouraging. So the next slide just summarises the conclusions from those data sets. No turbine-related changes in relative abundance for harbour seals, grey seals or porpoises. The actual sightings rates for grey seals or porpoises were much lower than those for harbour seals. So the power to actually detect changes was relatively low. And we have seen strong evidence of redistribution of harbour seals in the survey area during operation. The extent of it is relatively small, and it's unlikely to have major significant biological consequences. And this corresponds with what we've seen from the telemetry studies, which I'm going to go on and discuss now. So we've done, if we can move on to the next slide, we've carried out 3 separate deployments of seal tagging studies where the animals have been tagged with Sea Mammal Research Unit mobile phone tags that actually collect and transmit GPS quality location data, but also collect and transmit detailed dive behaviour and haul-out records of animals. In each case, these tags are attached to the seals in March, and they're glued onto the fur of the seals, and then they fall off when the seals molt in August of each year. So we carried out 3 deployments, one during the baseline period before the turbine was put in, one actually coincided with the installation period, and then the third deployment, which was just last year, coincided with the period of operation of the turbine. So if we move on to the next slide, this just shows a very kind of rough overview of the tracks from the 3 years. I just wanted to show across the 3 years there's a great deal of individual variation in behaviour, with some seals transiting to fairly far off haul-out sites. In all 3 years there was fairly good use of the haul-out sites inside and outside the loch, and on the coastline further away from the loch. And in 3 years, in all 3 years, there was a very similar amount of inter-individual variation. And the next slide, we're going to focus on the data from 2010. And I'm not going to say too much about individual slides. If Anna, you could just flick through these at a relatively quick pace. I think what I want to get across with these is just the amount of inter-individual variation. Some seals never entering the loch, never going past the turbine. Other seals spending vast amounts of their time in the loch or around the turbine site. This white one, for example, and other ones showing a mixture of movement in and out of the loch and to forage out at sea. This figure just shows all tracks overlaid on top of each other. And if we flick through those again, but this time we're just focusing in on the position around the turbine. And we can see some seals never going anywhere near the turbine, other animals spending lots of time transiting past. I'll point out at this stage that I haven't shown the detailed tracks for the other 2 years. The picture was very similar in the baseline period and during the installation period, where animals were actually, there's a great deal of variation in the amount of transit past the turbine site in all 3 years. So we've wanted to look at some metrics that actually told us something about how seals were behaving in relation to the turbine presence and its operation. So we focused on looking firstly at the rate at which seals transited past the turbine. One of the concerns about the turbine installation had been that given the unique situation of Strangford Lough with a breeding population, would be that the turbine would act as a barrier to seals moving in and out of the loch, and that breeding population would just either be isolated within the loch or animals would not transit back into the loch and be lost from that population. So in order to see whether that was happening, we looked at the transit rate of animals in the 3 years. And here you can see that there's quite a large degree of variation in individuals. The bar chart, each individual seal is a bar, so where there's no bar, there should be 12 in each year. So where there's a bar missing, that's a seal that never actually transited at all. There's absolutely no statistical difference in transit rate between the 3 years, but a very high degree of individual variation. In order to detect a change, given the data that we had, the change in transit rate between years would have had to have been over 5 times between years. But we can say that, what we can say is that there's definitely no out-and-out barrier effect, that seals are still transiting with frequency in the presence of the turbine. Next slide. So that was a broad look across years. We now wanted to look at how the rate at which individual seals transited past the turbine varied with the operation of the turbine. So we used data from 2010 and looked at the ratio of transit rate when the turbine was on relative to when it was off. And you can see here that only a handful of seals actually transited past the turbine enough times to actually make this comparison. But those that did, all bar one of the seals actually transited slightly less when the turbine was on relative to when it was off. Overall, there was a mean reduction in transit rate when the turbine was on of 20%, with confidence interval between 0.5 and 0.9 of a ratio. Okay, so next slide.
Carol, I'm just giving you about a 5-minute warning here.
Okay, sure.
Again, I'll just say for the participants, please start submitting questions if you have them now for Carol.
Okay, the next thing we then wanted to look at was the location in the narrows at which the seals were passing the turbine. So in order to do that, if you flip onto the next slide, what we did was we isolated the segments of track that had a location either side of the turbine, interpolated a straight line between the two, and where that line crossed an imaginary line across the narrows at the turbine, that was where we assumed the seal transited. Next slide. So we built up distributions of crossing location for each of the 3 years. And that's what these figures show. Each, the frequency on the x-axis is the number of individual seal transits. And the x-axis is the distance from the turbine. So where 0 is and where the 6 red dotted lines in 2008 and 2010, those show the position of the turbine, and the other 2 dotted lines show the extent of the channel. There are some errors in interpolation across land, and that's why there's some of those bars fall outside those lines. And although that looks quite a striking difference, statistically we couldn't detect a change, probably because of the fact that we're not actually looking at the same individuals in all 3 years. And in all 3 years, there was a big amount of variation in what individual seals were doing. So we're unable to actually detect a difference between the 3 years. But what we did also look at in 2010 was looking at the pattern, that pattern of crossing location in relation to whether the turbine was on or the turbine was off. And we saw no change in that pattern. So there was still that distinctly bimodal distribution of transit location, regardless of whether the turbine was on or was off. So despite the fact that there may not be a significant difference in the metrics that we looked at between years, there certainly seems to be some evidence of local avoidance of the turbines, with seals choosing to preferentially transit up the channels either side of the turbine. Next slide. So it's difficult to work out actually what the implications of changes in these metrics are. As I said, we didn't see any big changes in abundance of animals, but we've detected some slight changes in some behavior. What we don't know is whether all these transits are equally important. What we need to look at is potentially separating out transits, which are just movements from one haul-out site to another, from actual directed foraging trips out to sea, because the implications of reductions in one type of transit may be more than another. There's also starting to get some evidence for preferential location and local avoidance, which suggests that there's a non-uniform distribution of animals, which we can actually feed into collision risk models that are being developed to help parameterize them over and above assumptions that need to be made about uniform density. And we can also think about how the extent of local avoidance we might be seeing could potentially feed into array designs. Now, I'm aware that I'm running out of time, so I'm actually going to skip right through the last third of my talk, which was talking about acoustic monitoring of harbour porpoises. And if we could just skip right to the end to slide number 53, which is one of my concluding slides. And I'm happy to talk about the results of the acoustic monitoring to anyone who would like to get in touch. So from the strands of monitoring we've looked at, the sort of big picture that's coming out of the data is that the turbine generally is having a very low impact on the marine mammal populations. There is some evidence of local redistribution in the presence of the turbine, but we haven't seen any declines in abundance over the 5 years that we've been monitoring. We've seen a local redistribution of harbour seals in the water during operation, and a small reduction in seal transit rate while the turbine is operational. And though I didn't go into the results today, we have seen variation in harbour porpoise acoustic detections in relation to installation and operation, but the operational detection rates recovered after an initial decrease over the installation phase, and any changes there were very small in magnitude. So the next slide just wraps up a little bit about what we've actually learned about monitoring, which kind of hopefully is going to lead into the kinds of things you might be discussing in the next webinar, about some of the technologies that we've been using and some of the limitations that there may be. Static passive acoustics, we've had some issues with moorings, we've had high rates of pod loss, and we've had some issues with high ambient noise in the high tidal environment. On the active sonar front, we're developing some experience there, and we've realized that identification using the currently available technologies is challenging, and we're going to be quite reliant, I think, on the development of systems which can accurately recognize targets and potentially provide ID for species if that's to be used as a tool for monitoring the behavior of animals around devices. And because of the active mitigation requirement at CGen, we actually still know very little about actual collision risk. At the moment, there's still an exclusion zone, and the turbine is shut down if a marine mammal approaches within 30 meters. So we still don't know about that avoidance behavior to parameterize actual collision risk. We've often got a poor ability to detect any changes in an impact framework from shore-based visual observations. We need methods and analytical methods that can take into account spatial and temporal autocorrelation. And we need to think a bit more about what our definitions of significant impacts are when we're seeing small changes of behavior, and come up with a framework for potentially scaling up to population level consequences. Telemetry studies, we need to be able to get locations on a much finer scale than we can at the moment, and high levels of individual variability are an issue for detecting change and impacts with turbine devices. So I'd just like to end there thanking the whole host of people that have been involved in the monitoring from its inception. David Ainsworth at Marine Current Turbines, who's been instrumental at driving a lot of this work, and Marine Current Turbines and DEC in the UK for providing funding for most of this work. Thanks.
Great, thank you, Carol. What we're going to do is take 5 minutes for questions specifically for Carol, and then we're going to switch to other questions for other presenters as well. So if you have any great thematic questions that you want to have discussed, feel free to submit those now. We might go about 5 minutes over our allotted webinar time. I hope that's okay with people, but I want to give a chance for these questions to get asked. So, Carol, there are a number of questions coming in around the fact that seals have sort of behavioral traits that might be different than fish, and that they have natural curiosity and do other things that might be more unpredictable. And I'll try to go through those. I'm not sure if I can synthesize. The first one says, in many years working in the ocean, I have observed that porpoises and seals are playful to the point of seeking contact, while whales, for example, might keep their distance. And the question here is, while it might be possible to have some sort of an exclusion zone for large whales, or do something that could help them keep their distance, how do you keep playful animals like porpoises and seals away if they're naturally curious?
Well, at the moment, at the CGen turbine, the exclusion zone actually operates where if a target comes within a certain distance of the turbine is shut down, so it stops operating. So that risk of collision and direct impact is eliminated. But I get the point. In future, we probably don't want to have to rely on such strategies. We want to be able to develop devices and arrays where we don't have those strategies in place. And how that happens, I'm not entirely sure. Yes, seals, I've spent a long time working with captive seals and wild seals, and totally appreciate they can be very curious, playful animals. And how you mitigate against that is a really good question. I guess we have to sort of put it in the context of learning, and that once these installations are in an animal's environment, there'll be a certain degree of habituation to them, and that novelty won't necessarily be the case. So I think at each individual situation will be different. So I think it's going to be the development of appropriate deployment and adaptive management situations on a sort of case-by-case basis until we're in a position where we've learned a lot more about how marine mammals react to these devices in situ.
And the second question really follows on to that. Did you observe any learning happening over the course of your study?
We did look over, particularly over the 2010 deployment, for any changes in the metrics that we looked at over time. And we were limited by sample size somewhat in that, given the relatively small sample size of only 12 individuals, when we cut that down by the number of animals that actually transited regularly enough to yield data, when we started cutting that down more by looking at changes over time or differences between the sexes, we were really limited in what comparisons we could make. But we didn't see any obvious changes with the tagged seals over time in terms of how they were behaving around the turbine.
Great. Another question, did you see any data on strikes from the on-turbine stress gauge used by MCT?
No, as far as I'm aware, there's not been any detections of any collisions to date. Probably or potentially as a result of the mitigation strategy. Though I think we're getting to a point where the shore-based visual observations and the telemetry data, and we have looked at some of the target data from the active sonar, and our assessment of collision risk is probably now much lower than it was when the device was first put in place. So yeah, the quick answer is no. There's never been any collisions detected.
Okay. And I know we're cutting into our time for thematic questions, but another question on your study. You didn't get to your acoustic section, but with a high ambient noise of tidal flow, do you believe that your acoustic methods support a signal-to-noise ratio that allows you to see seal passage at high flows?
Yeah, the acoustic monitoring was for porpoise passage rather than seal passage, and that is a very good question. What we suspected might happen is that we would be getting a lot of fault detections during the high energy periods of tide, and little less detections at other times because of that false triggering. But that didn't actually happen, and what we actually got was a very, very strong diurnal pattern in acoustic detections. And the strength of that pattern and the strength of the seasonal patterns led us to conclude that the ambient noise in this situation wasn't giving us a large degree of false triggering of detections.
Okay. And these are just really quick. Let's see. Did you guys look at diving birds in your studies at all?
There were records of diving birds were looked at as part of the shore-based visual observations. I wasn't very involved in the analysis of those data, but I know that they are being looked at.
Okay. Well, at this time, there are a couple questions hanging on for Carol that we might be able to get to in written form, but I want to take the last bit of time to ask a couple overarching questions. And before I do that, Tim, you had a correction you wanted to make?
Yeah, if I might briefly. Somebody asked about my slide of results where it showed something like 98, 90, yeah, the upper right 98%, 99%, and then related that to no injuries observed. My explanation was that we censored that data essentially and chose the conservative approach. That was incorrect in those specific cases there. What we did find after 48-hour holding period was one dead smallmouth buffalo, one dead bigmouth buffalo in the treatment groups. So we did have 2 fish died after 48 hours or within 48 hours, but they didn't have passage-related injuries that we could observe. So that's the gist there. If that doesn't make sense to whoever asked that question, feel free to contact me directly.
Okay, great. Thanks, Tim. I've received a couple of questions on sort of in the thematic realm, and I'll try to aggregate those into one question. And there was a number of folks who commented that most of these studies are for one turbine, and questions around statistical significance. How do we take the data from relatively short periods of time and for one turbine and scale up to really tell us something about what an array might be or what effects could be over a longer period of time? And I'd like to open that up to our presenters. If there's if you have thoughts on that, please feel free to comment on that now.
Hi, Simon, it's Sue Barr from Open Hydro. Just to respond on the idea of scale, this is why we need projects in the water. We found that having something in the water at the European Marine Energy Centre has yielded initial results. It's given us numerical data to work with, but until we have small arrays and we can actually work on a monitoring package to look at those effects, then it will be very difficult to have any kind of linear scalage or any kind of, I suppose, robust statistical analysis of those results. We're putting an array into Paimpol in France as part of a project with EDF, and we have a monitoring package attached to that, which will start to sort of look at these kinds of effects. But I think the real point there is around the technology to look at these effects and really to pull out hard data in these kind of environments, but also having the technology in the water, the tidal technology in the water to look at things like behavioural ecology. So I think it's going to take a lot of cross-academia and industry collaboration in order to answer these questions, but certainly having projects in the water and having people developing the technology to look at these effects is very, very important going forward.
Ted Castro Santos here. Can you hear me?
Yes, go ahead, Ted.
Yeah. This is definitely a question that I've been really interested in and concerned with as well. I think some of the things that we do on individual units can be scaled up to the larger question, so that, for example, if you can demonstrate the ability of individual animals to avoid a unit or to pass through a unit safely without any sort of injury or delay, you can begin to extrapolate those kinds of results, or even if there are some injuries or delays associated with it, you can begin to extrapolate those results upward into the effects of an array. But some of the talk that we've seen where you look at the changes in behavior, those maybe point to things that we should be more concerned about also. So by doing some of this work on a smaller scale, you might begin to see some questions popping up that will help guide the way that you then approach the full-scale studies when they begin to be done. So these questions of avoidance or the inability to, unwillingness to pass a structure, or, like the idea of an attractive nuisance. If you're actually attracting animals to a single unit, you can imagine that if you begin to have lots of these units out there, that could create an entire shift in the ecology of the area where these units are being deployed. And so questions are, not that we're going to get answers this way, but I think we will at least begin to get some questions that will help guide us in future studies.
Thanks, Ted. Any other panelists have comments on that issue?
Yeah, Carol here. I'd just like to comment on the question of scale in another dimension as well. When we're talking about scaling up from individual level effects to detecting effects on individual animals or small groups of animals or a sample of animals, I think kind of what would be quite important for development to application to arrays and other devices in other places will be development of methodologies and frameworks for actually working out population-level consequences of individual-level effects, and in particular sort of sublethal effects such as displacement or behavioral changes. I think that's what we need to get a handle on, and what these changes actually might mean and the consequences might be for populations and conservation status.
Excellent. You may see up on your screen now a slide with some additional information. We can keep going on some of these Q&A, but I see people dropping off the webinar, so I want to make sure that you see that where you can find the presentations, when the next webinar is, and how to get comments to Anna. So please take a look at that. Other panelists, any other thoughts that you heard coming out of this, out of discussions you wanted to raise for the larger group?
This is Ted again. I have just one general observation, something that concerns me quite a bit in this whole field that's emerging, is that it's a common problem, I think, where we're seeing that we're having a hard time defining parameters, things that we're able to measure, that have tight enough confidence intervals around them to enable us to be able to detect an effect where it occurs. And I think we saw several examples of that today. So I think that becomes a challenge for us, is to work on focusing in our experimental design techniques so that we are able to detect meaningful effects where they occur. That's the one thing that really worries me, is that some of these instruments we're using are actually pretty blunt, and we might not be able to see important things.
Yeah, I would completely agree with that comment. And I think in a sort of regulatory framework as well, more appreciation of that needs to be sort of taken on board, and insistence on appropriate methodologies in assessing impacts and predicting impacts as well. So the measurements are made on appropriate scales, and an effort is made to take into consideration the levels of natural variations, rather than a one-size-fits-all monitoring requirement. That more attention should be given to the kinds of factors that will affect our ability to detect change going forward.
Great. This is Simon. I think what we're going to do is end it there for now and give Anna and Jocelyn the chance to close us off. I wanted to, again, thank you all. And as questions are coming in still, we're about done with ones coming in from participants, but please do get a hold of Anna if you have additional comments. We can get them out to the presenters. But Anna and Jocelyn, do you want to take us home?
Sure. Thanks, Simon. I just want to be sure to thank all of our presenters again for taking the time to tell us about their wonderful work today. I think it really gives us a lot to think about moving forward, and it's really a great discussion to have. So thank you again for participating today, and thank you, Simon, for helping with the moderating and questions and helping everything go smoothly. I just want to be sure that we mention that the projects featured today are not by any means a complete list of the research efforts going on in this area. And here on this slide showing now, we've kind of pulled up a couple other projects that we know of that are going on that relates to this topic of direct and indirect interactions between aquatic animals and MHK devices. And if you happen to know of any other studies going on in this area that you would like to bring to our attention, my contact information is at the bottom of this slide, and it's also on the webinar information that you received when you registered. So please contact me with any suggestions of projects that we can add here, because this is part of our goal in this webinar series, is to increase understanding on our side as well as the viewer side of what's going on, and increase awareness of this great work. And I also just want to mention again that the presentations that were featured here today and a recording, a video and audio recording from this webinar will also be posted on Pacific Northwest National Lab's TSIS site, which is their environmental MHK database. And this link is not the most up-to-date link, but I will be creating a distribution list from the email addresses of the people that registered for this webinar today and for our last webinar. And I'll be sending an updated link out later this week, within the next couple days most likely, with this updated link so you all can have access to this information. Our next webinar series will be Wednesday, September 14th, and it will go a little bit longer. We'll be having 6 presenters on that one, so we'll run till 3:30. And the topic will be on developing monitoring techniques and strategies for MHK devices. And again, any questions, comments, or feedback that you have is definitely welcome. And we encourage you to get back to us if you have any questions, comments, or feedback. My contact information is listed here again. And thank you for your attendance today, and we hope you enjoyed the webinar. Have an excellent day. Thanks.